Hello everyone! In this lesson, you will learn about another important class of asymmetric cryptography algorithms, the elliptic curve cryptosystems. This lesson will define elliptic curves in abstract algebra, give mathematical background on groups, introduce the arithmetic laws on elliptic curves, and describe their use in cryptography and security. Since their discovery, earlier asymmetric cryptosystems like RSA and ElGamal have become renowned for their ability to withstand attacks. They're being used every day on many devices and cover the current security standards. Modern developments in technology, however, and most importantly small Internet of Things devices and mobile handheld devices, have increased demand to secure communications generated by them. Because these devices do not have as much computing power and memory at their disposition, it is undesirable to spend a lot of resource and bandwidth on securing traffic. Desktop or laptop computers have no problems working with 2048-bit and larger RSA keys, but these small embedded devices require something more efficient. This is what makes elliptic curve cryptography stand apart from RSA, is its efficiency. Elliptic curve cryptosystems are supported in most main web communication technologies, like TLS, PGP, and SSH to name a few, not to mention Bitcoin and other cryptocurrencies. However, while the algorithm of RSA is relatively simple to explain and rough implementations can be created quite easily, as you have seen in a previous lesson, the foundations of elliptic curve cryptography are less known. Elliptic curves have been objects of intense study in number theory for at least a century. The use of elliptic curves in cryptosystems was proposed independently by Victor Miller at IBM Research and Neil Koblitz in 1985. Elliptic curves may come in many forms. For the scope of this course, an elliptic curve is a plane curve that consists of a set of points satisfying the equation y squared equals to x cubed plus ax plus b, together with a special point at infinity, usually denoted as O or an infinity sign. The equation here represents the Weierstrass form of elliptic curves, the most commonly used one. Other ways to express elliptic curves include the Montgomery form, Edwards form, and Jacobi form. Here is an example of an elliptic curve plotted over real numbers. Depending on the values of the coefficients a and b, elliptic curves may assume different shapes on the plane, symmetric about the x-axis. This curve in particular has coefficient a equal to -3 and b equal to 5. The curve should have no singular points, that is, no cusps or self-intersections. In cryptography, elliptic curves are defined over specific discrete sets of integers, called finite fields, which allow introduction of arithmetic operations according to the laws of underlying algebraic groups. A group G is a set of elements along with a binary operation that together satisfy the fundamental properties of closure, associativity, identity, and inverse properties. The operation with respect to which a group is defined is often called the group operation, and a set is said to be a group under this operation. The group operation is often addition or multiplication. An intuitive example of a group would be a group of integers with the group operation being addition modulo n. Let's use as an example a group with 5 elements ranging from 0 to 4 and the operation circle plus being addition modulo 5. Elements A, B, and C with binary operation circle plus form a group under these conditions. First is closure. If A and B are 2 elements in G, then the result of addition of A to B should also be element of G. You can see that closure is satisfied for the elements of our example group. That is, the group contains all the results of addition of any pair of elements. Next property is associativity. The group operation is associative if for all elements A, B, and C in the group, adding c to the result of a plus b is the same as adding a to the result of b plus c. And the associativity is satisfied under our example set and the operation being addition modulo 5. Other properties of a group are identity and inverse. There should exist an identity element E, also denoted as I, such that E plus A equals to A plus E equals to A for every element A in G. For our example group, and commonly for groups with addition operation, this element is usually 0, as adding 0 to every element of the group results of the same element. Next, there must be an inverse with respect to the group operation of each element. Therefore, for each element A in the group G, the set should contain an element B that is an inverse of A, such that the applying operation of A with this inverse results in the identity element. For example, the inverse of 2 under the addition modulo 5 is 3, since 2 plus 3 equals to 5, which is 0 modulo 5, and the inverse of 1 is 4. Additional properties that make a group a cyclic group are commutativity, that is, for all A and B elements of G, A plus B is the same as B plus A. That is, adding 1 to 3 modulo 5 is the same as adding 3 to 1, and so on for any element of G. Next property is generator. There should exist a generator element, such that repeated application of the generated on itself is capable of producing all the elements in the group. In our example group, such element is 1. You can obtain all the other elements of the group by adding 1 to itself repeatedly. So 1 plus 1 is 2, another time 1 is 3, another time 1 is 4, and so on. In a group defined over an elliptic curve, the elements are xy coordinates of points on the curve. The identity element is the point at infinity O, and the addition follows special rules to ensure all the preceding requirements, such as associativity and commutativity, are fulfilled. The curves used in cryptography are chosen to have a cyclic group, so there is a generator point that, added to itself many times, can produce every other point on the curve. The main operation involved in elliptic curve cryptography is point multiplication. That is, multiplication of a scalar k with a generator point G on the curve to obtain another point on the curve. This multiplication is basically applying the group addition of G to itself k times. Point multiplication can be achieved by two basic elliptic curve operations, point addition and point doubling. Point addition is addition of two different points P and Q to obtain another point R equal to P plus Q under the group operation. The following plot illustrates the relative positions of points P, Q, and the resulting point R of their addition on the plane curve over real numbers. Point doubling is addition of a point P to itself to obtain another point Q, so that Q equals to 2P. The following plot illustrates the relative position of the points P and the resulting point Q that is a double of P. Point multiplication of point P with the scalar k can be achieved by repeated point addition and doubling. For example, if k equals to 19, it can be written in terms of addition and doubling as follows. This method is called the double and add method for point multiplication. It is more efficient than simple repeated addition. In this case, it takes just 4 doublings and 2 addition operations to achieve k equals to 19 instead of 19 additions. There are other efficient methods for point multiplication as well. In the context of cryptography, one thing to note about elliptic curves is that they are neither elliptic nor curves. Elliptic curves used in cryptography are defined over discrete sets of integers called finite fields. For instance, here is the plot of the curve with the same coefficients -3 and 5 you saw before, but defined over a finite field modulo 503 with an operation in this field. As you can see from the plot, it is a collection of seemingly chaotic points, which is exactly the reason why it is useful in cryptography, like seeing pseudorandom number sequences. In a continuous curve, given a point, you know exactly where on the plane the next point is going to be. In a discrete curve, given an arbitrary point P, you know for sure that it can be reached from the generator point G by adding itself to so many times, but you don't know how many times. There is no efficient algorithm to find out how many steps are needed to compute P from the generator, but to sequentially try all 2G, 3G, Kg one by one until you get to the point P. The parameters for the curves used in cryptography are chosen to be large enough so that given a public key point P, it is infeasible for an adversary to perform an exhaustive search over all possible private multipliers to brute force the private key. For example, this is the equation of the curve used in Bitcoin. You can see how large the modulus is, and here is its respective generator point. This plot of the first 5,000 points on the Bitcoin curve from the generator illustrates how vast the space and how chaotic the disposition of possible points is. The coefficients of the curve equation, the field modulo, and the generator point are published in standards as recommended domain parameters. Since the curve parameters and the generator point are public knowledge, the secret used as the private key in elliptic curve cryptography is the multiplier k. And the public key is the coordinates of a point produced by multiplying this k with the generator point published in standards. Elliptic curves are used mainly for digital signatures, being standardized as Elliptic Curve Digital Signature Algorithm (ECDSA). Other digital signature schemes over elliptic curves include Schnorr and Edwards signatures. The Wolfram Language supports all the elliptic curves recommended by NIST Digital Signature Standard and a few more. Today, elliptic curve cryptosystems can be found on TLS, SSH, and other main technologies of the modern web and IT world. Elliptic curves are also used extensively by Bitcoin and other cryptocurrencies to secure wallets and authorize transactions. The security of elliptic curve cryptography, similarly to the Diffie-Hellman key agreement protocol, depends on the difficulty of the discrete logarithm problem, known as ECDLP. For elliptic curve, this problem is defined as follows. Let P and G be 2 points on an elliptic curve such that k multiplied by g equals to p, where k is a scalar. Given P and G, it is computationally infeasible to obtain K if K is sufficiently large. Thus, K is the discrete logarithm of P to J. The security of RSA depends on the difficulty of factoring large integers. Factorization can be done generally faster than resolving elliptic curve discrete logarithm, which means you can use shorter keys to provide security levels where RSA would need much bigger keys. For example, here are the default public key sizes generated. The elliptic curve public key can further be encoded to take as few as 256 bits and still provide security comparable or better than RSA with 2048 bits. When scaled to billions of secured connections, the difference in memory needed to store these keys is quite significant. This lesson concludes the section on asymmetric cryptography. In the next section, you will learn about important applications of various cryptographic algorithms.